The Richter magnitude scale assigns a magnitude number to quantify the energy released by an earthquake. The Richter scale is a base 10 logarithmic scale, which defines magnitude as the logarithm of the ratio of the amplitude of the seismic waves to an arbitrary, minor amplitude. As measured with a seismometer, an earthquake that registers 5.0 on the Richter scale has a shaking amplitude 10 times that of an earthquake that registered 4.0, and thus corresponds to a release of energy 31.6 times that released by the lesser earthquake. Development. In 1935, the seismologists Charles Francis Richter and Benno Gutenberg, of the California Institute of Technology, developed the Richter magnitude scale, specifically for measuring earthquakes in a given area of study in California, as recorded and measured with the Wood-Anderson torsion seismograph. Originally, Richter reported mathematical values to the nearest quarter of a unit, but the values later were reported with 1 decimal place. The local magnitude scale compared the magnitudes of different earthquakes. Richter derived his earthquake magnitude scale from the apparent magnitude scale used to measure the brightness of stars. Richter established a magnitude 0 event to be an earthquake that would show a maximum combined horizontal displacement of 1.0 micrometer on a seismogram recorded with a Wood-Anderson torsion seismograph 100 km from the earthquake epicenter. That fixed measure was to prevent negative magnitudes from being assigned. The slightest earthquakes that could be recorded, and located in that time, were around magnitude 3.0, however, the Richter magnitude scale has no lower limit, and contemporary seismometers can register, record, and measure earthquakes of a negative magnitude. Was not designed to be applied to data with distances to the hypocenter of the earthquake greater than 600 km. For national and local seismological observatories the standard magnitude scale is today still. Unfortunately this scale saturates at around =7, because the high-frequency waves recorded locally have wavelengths shorter than the rupture lengths of large earthquakes. Later, to express the size of earthquakes around the planet, Gutenberg and Richter developed a surface wave magnitude scale and a body wave magnitude scale. These are types of waves that are recorded at teleseismic distances. The two scales were adjusted such that they were consistent with the scale. That adjustment succeeded better with the scale than with the scale. Each scale saturates when the earthquake is greater than magnitude 8.0, and, therefore, the moment magnitude scale was invented. The older magnitude scales were superseded by methods for calculating the seismic moment, from which derived the moment magnitude scale. About the origins of the Richter magnitude scale, compare Richter said. I found a 1928 paper by Professor Kawadaty of Japan in which he compared large earthquakes by plotting the maximum ground motion against the distance to the epicenter. I tried a similar procedure for our stations, but the range between the largest and smallest magnitudes seemed unmanageably large. Dr. Benno Gutenberg then made the natural suggestion to plot the amplitudes logarithmically. I was lucky, because logarithmic plots are a device of the devil. Details. The Richter scale was defined in 1935 for particular circumstances and instruments. The instrument used wood became saturated by strong earthquakes and unable to record high values. The scale was replaced by the moment magnitude scale. For earthquakes adequately measured by the Richter scale, numerical values are approximately the same. Although values measured for earthquakes now they are frequently reported as Richter values, even for earthquakes of magnitude over 8, where the Richter scale becomes meaningless. Anything above 5 is classified as a risk by the USGS. The Richter and MMS scales measure the energy released by an earthquake. Another scale, the Mercalli intensity scale, classifies earthquakes by their effects, from detectable by instruments but not noticeable to catastrophic. The energy and effects are not necessarily strongly correlated. A shallow earthquake in a populated area with soil of certain types can be far more intense than a much more energetic deep earthquake in an isolated area. There are several scales which have historically been described as the Richter scale, especially the local magnitude and the surface wave scale. In addition, the body wave magnitude, and the moment magnitude, abbreviated MMS, have been widely used for decades, and a couple of new techniques to measure magnitude are in the development stage. All magnitude scales have been designed to give numerically similar results. This goal has been achieved well for, and the scale gives somewhat different values than the other scales. The reason for so many different ways to measure the same thing is that at different distances, for different hypercentral depths, and for different earthquake sizes, the amplitudes of different types of elastic waves must be measured. Is the scale used for the majority of earthquakes reported by local and regional seismological observatories. For large earthquakes worldwide, the moment magnitude scale is most common, although is also reported frequently. The seismic moment is proportional to the area of the rupture times the average slip that took place in the earthquake, thus it measures the physical size of the event. Is derived from it empirically as a quantity without units, just a number designed to conform to the scale. A spectral analysis is required to obtain, whereas the other magnitudes are derived from a simple measurement of the amplitude of a specifically defined wave. All scales, except, saturate for large earthquakes, meaning they are based on the amplitudes of waves which have a wavelength shorter than the rupture length of the earthquakes. These short waves are too short a yardstick to measure the extent of the event. The resulting effective upper limit of measurement for is about 7 and about 8.54. New techniques to avoid the saturation problem and to measure magnitudes rapidly for very large earthquakes are being developed. One of these is based on the long-period P wave, the other is based on a recently discovered channel wave. The energy release of an earthquake, which closely correlates to its destructive power, scales with the 3/2 power of the shaking amplitude. Thus, a difference in magnitude of 1.0 is equivalent to a factor of 31.6 in the energy released. A difference in magnitude of 2.0 is equivalent to a factor of 1000 in the energy released. The elastic energy radiated is best derived from an integration of the radiated spectrum, but one can base an estimate on because most energy is carried by the high-frequency waves. Richter magnitudes. The Richter magnitude of an earthquake is determined from the logarithm of the amplitude of waves recorded by seismographs. The original formula is, where A is the maximum excursion of the Wood-Anderson seismograph, the empirical function AO depends only on the epicentral distance of the station. In practice, readings from all observing stations are averaged after adjustment with station-specific corrections to obtain the value. Because of the logarithmic basis of the scale, each whole number increase in magnitude represents a tenfold increase in measured amplitude. In terms of energy, each whole number increase corresponds to an increase of about 31.6 times the amount of energy released, and each increase of 0.2 corresponds to a doubling of the energy released. Events with magnitudes greater than 4.5 are strong enough to be recorded by a seismograph anywhere in the world, so long as its sensors are not located in the earthquake's shadow. The following describes the typical effects of earthquakes of various magnitudes near the epicenter. The values are typical only and should be taken with extreme caution, since intensity and thus ground effects depend not only on the magnitude, but also on the distance to the epicenter, the depth of the earthquake's focus beneath the epicenter, the location of the epicenter and geological conditions. Based on U.S. Geological Survey documents, the intensity and death toll depend on several factors and can vary widely. Minor earthquakes occur every day and hour. On the other hand, great earthquakes occur once a year, on average. The largest recorded earthquake was the Great Chilean Earthquake of May 22, 1960, which had a magnitude of 9.5 on the moment magnitude scale. The larger the magnitude, the less frequent the earthquake happens. Examples: the following table lists the approximate energy equivalents in terms of TNT explosive force though note that the earthquake energy is released underground rather than overground. Most energy from an earthquake is not transmitted to and through the surface. Instead, it dissipates into the crust and other subsurface structures. In contrast, a small atomic bomb blast will not, it will simply cause light shaking of indoor items, since its energy is released above ground. 31.6227 to the power of 0 equals 1. 31.6227 to the power of 1 equals 31.6227 and 31.6227 to the power of 2 equals 1000. Therefore, an 8.0 on the Richter scale releases 31.6227 times more energy than a 7.0, and a 9.0 on the Richter scale releases 1000 times more energy than a 7.0. Thus, quakes using the more modern magnitude scales will denote their abbreviations, and those that have no denoted prefix are. Please be advised that the magnitude number displayed for those quakes on this table may represent a significantly greater or lesser release in energy than by the correctly given magnitude. Magnitude empirical formulae. These formulae are an alternative method to calculate Richter magnitude instead of using Richter correlation tables based on Richter standard seismic event. The Lilly empirical formula, where A is the amplitude of the P wave, in micrometers, measured at 0.8 Hz, is the epicentral distance, in km. For distance less than 200 km. For distance between 200 km and 600 km. Where A is seismograph signal amplitude in m, d distance in km. The Bistrick-Zini empirical formula for epicentral distance is between 4h to 160h. Where is magnitude, is the duration of the surface wave in seconds, is the epicentral distance in degrees. The Tsumura empirical formula, where is the magnitude, is the total duration of oscillation in seconds, is the epicentral distance in kilometers. The Tsuboi, University of Tokyo, empirical formula, where is the magnitude, is the amplitude in is the epicentral distance in kilometers. See also. References. External links: IRIS Real-Time Seismic Monitor of the Earth, USGS, Magnitude and Intensity Comparison, USGS, Earthquake Magnitude Policy, USGS, 2000 Euro 2006 Earthquakes Worldwide, USGS, 1990 Euro 1999 Earthquakes Worldwide, Alaska Railroad Earthquake with a table of yield to magnitude relations. Earthquake energy calculator with seismic energy approximated in everyday equivalent measures.